In this series of videos I'm attempting to repair this Elektronika D3 Nixie tube calculator built in the USSR back in the 1970s. Desktop calculator, 14 digits, but this one, as you probably saw in the previous videos, doesn't work. Doesn't really do anything at all other than light up the display. None of the functions work, although pressing certain keys does have some influence on the calculator. It might blank the display, for example. So in the previous videos I went through, dismantled this, cleaned up the backplane, cleaned the edge connectors on the board, replaced the caps in the power supply. Didn't really make much difference. Brought a few of the digits back to life that weren't working. They were fairly simple faults. But at the time I didn't have a schematic. Now someone that was watching the video was kind enough to send me a set of schematics that almost match this machine. Not quite the same, there are differences, but it's very close, so that's extremely useful for fault finding on a piece of equipment like this. Another viewer was kind enough to point me towards a data book for the ICs used in this machine, so again this is extremely useful. Unfortunately the IC markings don't match what's written in the data book, even though the devices are pretty much identical. So I've been going through and trying to identify what each particular device is and find the reference for it in the data book. So again, that was extremely useful. And so once I've got that information, the next step is to how to go about fault finding on a device like this. Now I've repaired a lot of calculators, mechanical, electronic, so they tend to have a lot of similarities in terms of the basic building blocks that they have. So it's really a case of identifying what those are and then also working out the interconnections. So in this case there is an interconnection chart that's included as part of the schematics, and each of these columns is one of the connectors for the board. So there's one of these for each of the boards, so board 1, board 2, etc. And again, someone was kind enough to help me translate part of this. Extremely useful. Had a lot of assistance and very nice feedback so far working on this. And so what we've got out of this so far is, because this is all handwritten, you really need a native speaker. It's all in Russian. You really need a native speaker to be able to make sense of this. And although you can make out certain letters, just making out letters of a foreign language doesn't mean you can read what it says. But he was kind enough to translate this, and so what I have now is a list of what each of these headers actually means. So I've annotated the schematics, so I now know what each of the boards is supposed to do. That makes life a great deal more straightforward. And also he was able to read the headers in the table, so now I know what these columns are. And basically they are, the board's got a front and back and a left and right connector. So the board's spun round in the machine, so connector A is the one on our right here. It's the one on the left as you look at the component side of the board. And the connector pins, in this case from right to left to right when we spin the board around, are numbered 1 through 22, and the first column after that, from the right to the left, is the signal name for that pin, and then the next column along is the destination for the backplane connections. In other words, this pin is connected through to this pin, and although you can't read it, the designations are board side pin number. And on the other side of the board, the back side, the side that's now facing us, they are letters. Now they're in Russian, but they are in sequence, so it's fairly easy to read. And then these black lines are just the interconnection buses. So now I know what all this information is. It makes life a lot easier, and I have traced a few of these through and it does actually work. So E2, for example, if you trace it through, it goes through to the E2 connections on another board. So that makes life a great deal more straightforward. So armed with this information, I was able to start fault finding, and what I started doing was I decided to start with the front board, just really as a sanity check to make sure that all the information I'd gathered so far made sense. Also, because the boards are conformally coated, it's very difficult to probe them with a scope. So I've got the riser that I made, and there's a second set of contacts on the riser, but I can use those as easy connections to the in-out connections for the board. And as I've said previously, looking at the in-out connections for a board is a kind of shortcut to try and figure out if there's anything obviously wrong with the board, because if the outputs are all working, there's no point going back into the board, because chances are the board itself is working. Doesn't guarantee it, of course. It might not be doing exactly what it's supposed to, but it's a good starting point. So that's what I did with this particular board. Checked all the interconnections, made sure that the information and the assumptions I'd made worked, and went from there. Now this is board 1, this is the front board, and I couldn't find any faults with this. I also used this to confirm the assumptions I'd made as to which chips were which. Like I said, the part number on the chip doesn't match what's in the data sheet, so I was just making sure I was properly identifying what each of these devices was in the data book, so I knew what the output should be relative to the inputs. Once I'd done that, I started thinking about the overall operation of the machine. And as I've said before, thinking about what the machine is supposed to do is a very good starting point for figuring out if there are any faults in it. Now if we turn this on, although you can't see the display, then it initializes, all the digits come up but all the decimal points are on, and pressing certain keys will cause the display to go blank. I press clear, it clears it. Also, I noticed when I was going through board 1 that pressing any of the keys, and this is the front board is a read-write, it's basically the buffer between the machine and the keyboard, so it's basically scanning the keyboard in effect. But pressing any key caused the correct output to change, so I'm fairly confident that the overall machine is working to a certain extent. Also, if I remove board 4, and if we just grab the schematic for board 4, notice it's identified here as the microcode unit. So this is really the state machine microcode, and it's basically a sequence controller. Depending on the inputs, it will go through a certain sequence of outputs, and it allows the machine to kind of make decisions based on certain of the inputs. And because the rest of the machine seems to work, I took this board out, and I showed this in a previous video, and if I do that, if I then press the 5 key for example, I get 5s all across the display, so every digit shows a 5, and it will do the same if I press a 1. It won't clear, I have to power it off and power it on again each time, but each time I press a key it shows the correct digits in all the correct value in all the digit locations. So that tends to indicate that the machine, not only is the register system working to a certain extent, but it can also properly identify individual values and properly interpret those. So a huge amount of the machine is working, so I suspect there's just sort of 2 or 3 ICs that are at fault. Could be more, depends on how the overall structure works. But that led me on to think, well, the next thing to look at is this microcode unit. It seems the best starting point, because it does look like it's failing to run through the process correctly. It's not a case of it's giving the wrong values as the result of calculations. It's just getting stuck when we try and do anything. So this is where I decided to start, and for reasons I explained earlier, I decided to look at the inputs and outputs. So I'll show you what I found so far. I'm just going to spin the machine round. So you'll find this fairly hard to see, but I started scoping the various outputs. And when I got down to this one, which is identified as not 32, so that's B pin 6, which is, be careful I touch here, there's some high voltages in this. So if I show you a value that we should get and press a key, Hopefully you can see that on the scope. You see we're getting an output, and I've got the scope set up so that the output values, if I find another low value such as there, you can see that the low values, which is actually logic 1 in this case, uses negative logic, is down towards the bottom of the screen on the scope. Whereas if I probe this particular pin, notice it's neither a 0 nor a 1, and that is this output here. And if we follow it back, it goes to this IC, pin 7. Most of these devices have complementary outputs. In fact, they all do, but they're not always used. But if we look at the complementary output of that device, which is used in this case, it goes through to B5, and that's the one that actually works. So if we put the scope probe on there and I press a key, notice we're getting a decent signal. If I go through to the other output, the complementary output, that's the one that's not working. So clearly that IC is not working. It could of course be that the output is being held by something or pulled high, and I followed through the chart that I showed earlier, and it just goes through, and the only connection to that goes through to the adder board, which is board 2. So I pop that board out and this pin still does the same thing, so this device is definitely faulty. I went through then and looked at other similar types of fault, and I found a similar problem on another board. Let's grab the schematic for that one. And for similar reasons I started doing the same thing with this board, and I found another faulty IC. It's doing pretty much the same thing. One of the outputs isn't working whereas the other one is. So it's quite a good way of spotting an issue with this type of device that has complementary outputs, because if one output's changing and the other isn't, you know that the device is faulty. So it's not like having to decode the inputs. So I'd gone through, started looking at all the various ICs, and decided it would actually be nice in this case, at least for the sake of the video, to attach the logic analyzer to just clarify what I've shown here. Okay, now one of the problems attaching a logic analyzer to these boards is, as I mentioned earlier, they're all conformally coated. So let's turn this off. And because they're conformally coated, it makes probing them quite difficult, and when I was probing with the scope I was having to press fairly hard with a specially sharpened probe. But what I've done is I've stripped the conformal coating off this particular board, or at least off the IC side of the board. I haven't done the other side. And someone's bound to ask, so the way I did that was, in this particular case, I used some cellulose thinners, put about a 3mm puddle of it in a tray, sat the board ICs facing down in that for about 15 minutes. It won't dissolve the conformal coating. In this case it loosens it, and how you go about this depends on the nature of the conformal coating, but they use the kind of cellulose lacquer on these, so it won't really dissolve it, but it will loosen it. You can then effectively wipe it off, and then I use a very soft brass round brush in a kind of Dremel tool, and you can just polish the pins and get all the remaining coating off them. So what I can do now, I get the multimeter, and what I can do is, even with a very gentle touch now, I can probe the pins. So the coating's gone off the pins. If I need to, when I finish, I can recoat it, but it means that I can now put a clip on there for a logic analyzer. So I'll get the logic analyzer set up, and we'll see what signals we're getting on this and see if it matches what we've found so far in trying to identify the faulty devices. I've got the logic analyzer attached. I'm using knife edge IC test clips here, and the way I've organised this is, as ever, I've created a set of test configurations for this particular project, and all they really are is the probe is set up in a kind of generic way in terms of its connections, and I've created a configuration for each of the logic elements that I need to test. There aren't actually that many different ones in this machine. There's a lot of ICs, but not that many different types, and this means that I don't need to keep swapping the pin arrangement on the test clip. I can just move it from IC to IC, test all the same types, leave the connections as they are, and then select the other configurations within the logic analyzer. Makes it very quick and easy to test this sort of thing, and also it will confirm my assumptions about what each device actually is. I've identified a couple of different types, and I've got written down here what's on the actual IC. It's not what's written in the datasheet, and then the UK or English version of that. So the next thing is to get this powered up, and we'll do a bit of testing and see if we can get similar results to what we found with the scope and identify the faulty components. Looking at the logic analyzer screen, you can see I've got this one set up, and this is for the 172M1 device. So this is a dual 4 input NOR gate. So I've got the 2 inputs set and then the 4 outputs. Remember that there are complementary outputs for each of the 2 sections. So we've got a Q and a not Q for each one. Also remember, this is a negative logic device with fairly odd voltages. So I've got a custom threshold set of -5 volts. So although these run at -27 volts, the high level threshold, that's the naught logic level, is anything higher than -2.3 volts, whereas the logic 1, which is a lower value in terms of voltage, is anything below around -7.5 volts. So I've set -5 volts because that's in the middle of that range. So just a word of caution, if your logic analyzer can't handle large voltage swings, don't connect it to a device like this. You could destroy it. So for example, if you have a TTL style logic analyzer, then connecting it to this type of machine will kill it. This particular analyzer can handle input voltages from -40 to +40 volts, so it's perfectly safe to use on this particular machine. I've got the trigger set up for this test. I've just got it looking at the Q output on the first gate, and if that goes high, it will trigger the analyzer. So we'll arm the analyzer. The calculator's already turned on, so I'm just now going to press one of the numeric keys. I'll press the 8 key, and you can see that's triggered the analyzer. And what we're looking at here, remember, is a pair of 4 input NOR gates using negative logic. So the top value, let's start off at E, is the 4 A inputs, and being E, of course, it means that one of them is low, and if we follow this across, at some point they all go high. That means that the inputs are all in the same state, and so the outputs change. And the important thing here is both outputs change, and they are complementary, so one goes from high to low, and at the same time the other one goes from low to high. So that's clearly working. The second gate isn't doing anything because the inputs aren't changing, and so this appears, at least superficially, to be doing what it's supposed to. If I want to change to a different device type, so in this case, let's say I want to change to the M2 device, the way I have this configured is I can just select that from my list of pre-configured devices. And notice the format now matches the M2 device. So if I just turn the calculator off I'll move the test clip onto an M2 device and we'll have a quick look at one of those. Turn it back on. Okay, so we now have the analyzer set up to look at an M2 device. So I didn't edit the video there. That's as long as it takes to swap it over. And we can now rearm this. I'll press the key again. And again, you can see that device is doing what it's supposed to. That particular device is a 10 input NOR gate. So again, the values we're seeing make sense. When all the inputs are high, the outputs change state, whereas when one of the inputs is low, the outputs change to the other states. But both outputs are changing and they're complementing each other. Therefore, that device, again, at least superficially, appears to be working. What I'm going to do now is go back to the device that I identified as being potentially faulty, and we'll have a look at that and see what the analyzer makes of it. Okay, I've moved the test clip onto the device that we saw or thought was faulty when using the scope. We'll rearm the analyzer, and as you can see straight away we have an issue, although the analyzer was triggered straight away, presumably because the output is in the state that I've got the trigger set to. So remember, the trigger was set to give us a particular trigger depending on what the output level was. But now notice that the problem we've got is both outputs, the Q and the not Q, are both showing as 1, and that's what we saw with the scope. We saw that one of the outputs was working but the other one wasn't. So clearly we have an issue with at least one IC on this board and one IC on the address latch board. And the problem I have now is, of course, getting hold of spares. Not too long ago it would have been fairly easy to just go online and purchase some spares. They are listed as being available. Unfortunately, with things that are going on at the moment, it is pretty much impossible to get any spares shipped from the only sources I can find. So once again, this project looks like it's going to go on hold for a while until either things settle down or I found an alternate source for these parts. But this is the way I'm going about this. If ever I find a way of getting the parts, I'll swap out the ones I found so far that are faulty and then continue the process. And it's exactly the same thing, just following through what's working, onto the next step, get that step working, and then hopefully by the time all the steps in the process are functional, the machine should start working again. It's just unfortunate that at the moment I can't get hold of any spare parts. So if ever I get the parts, I'll get back onto this project. Not quite sure when that will be, but it's certainly a fascinating project. Incidentally, if you do get an issue like this and you're working on one of these and it's only a single fault, the easiest thing to do, because these are complementary outputs, is you can just use a couple of transistors, use the output that is working, make a small inverter circuit and disconnect the original pin from the board and make your own gate. Unfortunately, because there's probably at least 3 or 4 faulty ICs on this, maybe more, it's not the approach I'm going to take here, and also it's not really my goal for this machine. I want to try and repair it as close to original as I can, which means holding out, and hopefully I'll find some ICs. I may look for a scrap machine if I can find a scrap machine that uses similar parts. These were fairly common parts and they're in lots of different pieces of equipment. If I can find any spares, I will of course swap it, and we can get back onto this project.